Okay, we're starting about. We're going to talk about electromagnetic induction today. Essentially, what this is, this was discovered by Michael Faraday. Okay, Faraday. Oh, it's right, neater than that. Michael Faraday is one of the biggest rags to riches stories in all of science. He was born to, I think, like a cobbler or a leatherworking family, and he just started taking the tools and tinkering on his own and messing with stuff, and he got really, really good at it and made all kinds of discoveries on his own. But back in this time, you had to be, for you to be taken seriously, you couldn't possibly have been of common birth. You had to have been of noble birth for your, just because you were lower class than everyone else. And so, the weight of your words were less just because you weren't born to a higher station, which is kind of BS. One and two, it's one of the reasons why we founded this country, is so that you wouldn't have those inherent barriers to doing well, just because of where you were born and to whom you were born. Although we're doing a really good job of reestablishing that again. So what Faraday was able to do was he did a lot in the field of electricity and magnetism, and in particular, he discovered that when you have a moving charge, will create a magnetic field. Okay, or more to the point, a moving charge, or I should say a changing or a changing electric field will create a magnetic field, and vice versa. A changing magnetic field not will create a changing, will create an electric field. Okay, which can also be called a current. Okay, so think about the uses of this. That if we can change an electric field or like move a bunch of charges around, we can create a magnetic field. Okay, so we can create a region that will behave with magnetic properties. Okay, or if we move a magnet around, if we spin a magnet or we do something like that, and we change a magnetic field, it can actually create a current. Well, this in particular, okay, is how generators work, electric generators. We take a magnet and we spin it, and we use force. Okay, so we use some kind of mechanical means to spin a magnet, and the magnet then generates electricity. So if you hear gas-powered generators, what they're doing is they're spinning a really powerful magnet around, and with a whole bunch, we're going to get into this a little bit more, with a whole bunch of loops of wires around it, and the loops of wires start creating an electric current that we can use to run our electric devices. Okay, and this is scalable to massive sizes, to the size of dams and nuclear power plants, are all based on this particular concept that we can change a magnetic field to create an electric field. Well, to understand how this works, we need to go back to the idea of a magnet. Okay, and we draw the field lines on a magnet, and they're going to look kind of you guys remember this? Okay, Now, we talked about this before, that there is no... whenever you have a north pole, you have to have a south pole. Okay, there is no way that you can chop this thing up and just get a north end, because the other end will always be south. Okay, whereas in electricity, we can have what's called an electric monopole, where you can have something with just one charge, okay, just a negative charge or just a positive charge. It doesn't work this way with magnets. You're going to have both ends to it, and because of that, you always get these loopy field lines. They always curl back onto themselves, or towards, the north end of some other magnet over here. But what we do have is we can take a cross-sectional area through here, and we can start measuring the amount of lines that are going through, measuring the amount of field that passes through this area. You guys follow me there? Yeah. Okay. And this value, the amount of area, amount of magnetic field, okay, that passes through an area, okay, is called magnetic flux. Okay, and it's usually about this time that I have to field questions about flux capacitor and that sort of thing from Back to the Future. And no, that doesn't exist. There's no such thing as a flux capacitor. There is, however, there's flux. There are capacitors, but there's no flux capacitor. Like you can pick your friends and you can pick your nose, but you can't pick your friend's nose. What's that? Magnetic flux. Magnetic flux, and it's given by the symbol phi. Okay, it's an I with a circle, or a circle with an I, however you want to write it. Okay, and this is given by the area, this area that you're talking about, times the magnetic field that is inside that area. Okay, and the unit for this is a Weber. Okay, it's not Weber, it's Weber. It's the guy who it was named after, Weber. And it is 1 Tesla times a meter squared. Now, that's not really important. This whole part isn't really important. This is the important part, the fact that it is flux, that there's a flux going through it. I'm sorry? Meter squared. Tesla times a meter squared.
What is a Weber?
That is it. The unit is a Weber. The unit for magnetic flux is called a Weber. Weber. Yeah. Okay. So, remember how we established a magnetic field and we talked about vectors going into the page and out of the page? Yeah. Okay. So here's what we're going to do. We're going to create a magnetic field that in this particular case is going which direction? Well, remember what these symbols look like. Okay, that if it's an X, it's the tail feathers of an arrow, right? Which means it's going away from you. And if it's a dot, okay, as opposed to dot, 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 right? This would be towards you because you're looking at the point of the arrow, right? Yeah. Okay, so this would be away. This would be away from you, looking. Okay. Now in this field, we're going to draw, okay, an area, a loop of wire. Oh, sure. How's that? So we draw this loop of wire. Okay, so just for demonstration purposes here, I drew 25 field lines, magnetic field lines, right? Okay, but what would actually be the flux through the loop? Okay, it would just be 9, right? Because there's only 9 lines inside the loop. Yeah? Okay, so that's the idea of what's going on here. Okay, what if I turned the loop? Okay, so here's the thing. We need to start thinking in 3 dimensions here. All right, this is beyond, it's not just 2-dimensional stuff moving around anymore and forces acting in this direction, that direction. Okay, we need to start thinking 3 dimensions. So let me see if I can get an example here. So I'm going to create here's what I'm doing. I'm creating a loop of wire. Okay, pretty close. So here's my loop of wire, right? What if I start spinning this? Okay, so here's the loop. If it's just laying flat, it's got, let's see, this one looks like it can hold, what, 6 loops? Or 6 lines? But what if I spin it? How much is passing through? It's less, right? Okay, now, did the area of my loop change? Okay, my loop is still the same, right? So if I turn it, okay, then the flux going through the loop decreases because the cross section of the loop is less now. You guys follow that? That we less can actually get through it. That our shadow looks different. So to the point where if I go like this, right there. Okay, what's my flux through that? 0. Well, it so happens, how am I holding my loop compared to the paper? Okay, it's perpendicular to it, right? Okay, so if our loop is perpendicular to our paper, then we don't have any flux going through, right? And if the loop is right, hold on. If our loop is parallel to the lines, right? So here's the plane of the loop, and the lines are going into the paper. If this is all parallel, then there's no flux going through. Here, if it's perpendicular, then we have maximum flux going through. You guys follow that? Okay. So what happens if I spin the loop? What's happening to the amount of flux going through? It's changing. A changing magnetic field will create an electric field. Oh. So if I start spinning this through my magnetic field, guess what happens to what's going on in the wire? Guess what starts happening in the wire? We get a current. We actually get a current coming in and out of. All right, we get a current coming through the wire because our magnetic field is changing. And if we do it fast enough, like say 60 times per second, right? That becomes that's actually what our frequency cycles at. Is that our frequency has a 60 hertz is the frequency of our current that goes through. Okay, so here's Faraday's law. Okay, and we're just going to write this out. Faraday's law. Faraday's law, yeah. I just need to start writing bigger. All right. Yeah. Okay, so if the flux through a given area changes over time, a voltage will be induced in the wire and a current will momentarily flow. If the number of turns in the wire, number of turns of wire, in the wire, and a current will momentarily flow. If the number of turns of wire is increased, okay, the voltage will increase proportionally. Yeah, is that better? Okay. So here's the idea. We take our loop of, see if I can make this a little different. So here's our loop. Okay. If I were to make a wire come in and go around, make a few more loops and then go out, the voltage will increase proportionally to the number of loops that I have. So if I had twice, if I put another wire in there, it would double the voltage. Okay. If I put 3 loops of wire, it would triple the voltage. Okay. 5 loops would quintuple the voltage. Right? You just multiply it by how many loops you have that are doing the spinning through the. Okay, we got this? Okay. Now, if you look over there to the AP wall of, okay, over on the right, you'll see where it says Faraday's law, and you got a whole bunch of fancy stuff. And it looks like this. It is. What's that? No, it's called an integral sign. Just go ahead and draw it in there. But the whole point is that this right here. Right. No, I'm not worried about you knowing what it is. You don't have to know what it is. I'm not expecting you to know exactly what it is. Okay, but this is for some of your benefits for those of you that are going to move on next year for your math. Okay. Mm-hmm. Okay, this, this is essentially what it boils down to. This winds up being the voltage divided by the number of loops. Oh. Okay. You should copy this into your notes. This is Faraday's law. Okay, this is his equation. It's Faraday's law. Okay, it's called Maxwell's equations of electromagnetism, and it's the discovery of these is foundational for the entire field of electromagnetism. In fact, they proved that electricity and magnetism were two sides of the same coin. This is the phi that we talked about over here. Yeah. Some you can just draw an O with a line through it. Okay, you don't have to do the. This is fancy, with the tops, with the top and the bottom to it. You don't have to do it. Okay, this equals the change in our flux over the change in time. Okay, or to rewrite it, voltage equals our number of loops, change in flux over the change in time. Okay, this is the induced, and that I wrote that really poorly. This is the induced voltage. Okay, which brings us to our next law that we've got right here. You've got this? Yep. Okay, now we have Lenz's law. What's that? No, that's that. Now, mind you, you don't have to know the integral over the EDS. You don't have to do that. You don't worry about that. I wrote that on there because that's officially what Faraday's law is. You guys know what we're learning here the version that we learn is for more specific cases, and that's the general case. Okay, so you don't have to do all of the. You don't have to worry about the integral EDS, that sort of stuff. Okay, so where's toe? Okay. Okay, we're just continuing here. This is Lenz's law. Okay, an induced voltage always produces a magnetic field that opposes the field that produced it. Okay. Now we're getting into, now we need to start thinking here. Okay. So an induced voltage always produces a magnetic field that opposes the field that produced it. Okay. Remember we talked about the right-hand rule, and when a charge moves through a magnetic field, it curves? Yeah? Okay. We have to apply the same idea here but go backwards with it. That if we're going to produce, okay, so in other words, the original magnetic field okay, is going to go through our loop here. Let's make our field again. Okay, and then we're going to make a loop. Okay, and we spin it, and it doesn't matter which direction it spins. The direction of the rotation of the direction of the rotation doesn't matter. Clockwise, counterclockwise. Okay, what matters is if it increases or decreases the area, okay, that's going into it, and which direction the magnetic field is. Yeah? Okay, so if we start spinning this, okay, if it's perpendicular now, that means we have the most flux possible. So if we rotate it, we're going to decrease our field, right? You guys follow me here? If we turn it, we're going to decrease the amount of field going through it. Okay, but that field is going in this direction. The current that is produced will go in the opposite direction to the change. So think about that. Our field is going this way, into the page. If we decrease it, that means the direction of change is actually in what direction? It would be up, right? So think about number line. So if we have if we're starting over here, okay, if our field is actually in the negative direction, but we decrease the amount of field going through it, it's really moving closer to zero, right? Same thing here. If this is going away from us, okay, but we decrease the fields, the change is really in the up direction. Yeah? Okay. Let's say you're accelerating. Right? Your velocity is increasing away from you. Okay, and then you step on the brake. You decrease your acceleration. Okay. What direction is your acceleration now? Your change in velocity is in the opposite direction to where you're going, right? Same idea. So here's our where the right-hand rule comes into play. We need to create a magnetic field that's going out of the page. Okay. So here's how it works. Take your fingers. You're going to grab the loop. Okay, and you're going to grab the loop, and you're going to create a current, okay, which will be represented by your thumb. In fact, let me throw this up here. Where are you? Oh, where are you? Where did you go? Why aren't you there? I need to find you. Oh, because I moved it. Shoot. Okay. Well, we'll just have to go without. Okay. So let's say you grab this. Okay, and what is it going to take to create? How are we going to get our fingers? Okay, so let's just do that. Let's draw a hand. Okay. Pretty crappy hand. Okay, this direction, the direction of our fingers, is our magnetic field. This is our current. Okay, so we stick our thumb in the direction of the current, or our thumb will be in the direction of our current, and the magnetic field is going to be how we curl our fingers. But we can curl our fingers so that they are going the direction we want them to inside the loop. Right? What direction do we want them inside the loop? We don't want them down. We want them up because it's going to oppose the change, right? So if this is decreasing, we need to do something that will increase the field, so our fingers are going to be going up, right? Well, if our fingers are up inside the loop, our current will be that way. Right? But what if I do it around this wire? What if I grab this wire? If our fingers are up, our current's that way. Here in this wire. Well, funny how that works, because that creates our circuit as we move around the loop. You guys follow me there? Okay, so we determined that we need if this is decreasing, okay, the current that we're going to do is going to increase, is going to oppose the field, right? So if this is a decrease, opposes the field that produced it. If we spin, the field is decreasing. Oh. Poop. It's the other way. The field that produced it is a decreasing field, which means it's going in this direction. We need to do something that's going to oppose the change, so we need our fingers going down into the loop. So, forget the black ones. Go with the purple ones. We need our fingers to go in the same direction. If this is, you guys follow me here? If this is decreasing, that means the field that's making the change is going up. We need to do something to oppose it, which is going down. Usually, it's in the same direction as the field that's going, unless we start increasing again, in which case it reverses. All right. So in this case, we would need our field to go down, our fingers into the page, and we'd start getting a current like this. Okay, this is something that takes practice. Okay, it takes practice to figure out which way our current goes. Okay, but this is the idea of Lenz's law, and this is what this is how we create a current in from a loop in a magnetic field. Okay. Last thing is transformers. Okay, they are more than meets the eye. Okay. All right. A transformer is a device that produces a change in voltage in an alternating current. So, we're going to have an iron core we're going to have some wire. Okay, an iron core with some wire. Okay, the voltage produced, so we're going to call this the primary, and this is the secondary. The voltage over the primary divided by the number of loops, okay, the number of turns in the primary is equal to the voltage of the secondary divided by the number of turns in the secondary. So I actually happen to make the same number of turns. 1, 2, 3, 4 turns. 1, 2, 3, 4 turns. So I probably should have made a couple more. Okay, this can also be written as Vp over Vs equals Np over Ns. It's an equivalent proportion there. Okay, so if the primary coil has more turns than the secondary coil, the transformer will decrease the voltage and vice versa. So that's why we have, in your neighborhoods, that's why you have the transformers, right? Those boxes that are up on the power lines, or just the ones that are at street level if you have underground power lines. And what these do is you have a massive amount of voltage driving into your neighborhood at these transformers. Okay, huge amounts of voltage. What the transformer does is it steps it down, and then sends out current to your house at 120 volts rather than the thousands of volts that are coming in to your neighborhood. That makes sense? Okay, so if you were to plug something in, let's say you weren't to have this, and it had all of our houses hooked up to the voltage at which we transmit these lines. Okay, you plug something in, and it's just going to absolutely blow up whatever you're plugging in, because the energy pushing your electrons through your device is going to be huge. It's like drinking from a water hose, fire hose. Okay, what the transformer does is it dials it down so that it's a more reasonable surge of energy that's powering that's supplying your device. Okay. All right, and that's also why you have little devices. You know, the little blocks of stuff that you plug things into when you, it's this thing. It's the when you buy an electronic, you get your plug. All right, looks like this, and this is what you plug into the wall. Okay, and you get all right, and you plug this into your. You plug this into your device. This is also a transformer, but this takes it from your wall current to a voltage that your phone can handle, which is even lower than that. Okay, so it's another kind of transformer. All right. Okay, your homework tonight is to copy the solved examples into your notes. Okay, there are 3 of them. Work yourself through it. Okay, in fact, that needs to go in your notes, and you guys need to complete don't want to do all of it. Yeah,